So you might recall last lecture we looked at this. Remember how velocity breaks up. This is my vector. My vector is right there. And it breaks up into the vertical component that actually makes sure how much time you're in the air, and the horizontal component, which affects how far you go out on that. So we're going to look at some things by getting out. You want to get out back to 3.2, which looks like that. 3.2 is the one where you did all the vector, the resolution, and you did find the resultants. So we have these two vectors. Now remember, horizontal component, we take the ideal case. We neglect air friction. So is anything ever going to change the horizontal component? Does it ever change? The out part, does it ever change? No. No, so 5. It's 5 here in the beginning. Now remember, this is how he threw it, but if we look at this, there's that initial vector. Right like that. That's the actual thing he threw. 5 there, but it's 5 here, so it means up here it's going to be a right here. So 5, 5, 5. There, horizontal never changes. It's 5 here at the top, still 5 horizontal. 5 horizontal. 5 horizontal. We should be filling in this information as we go along, because you're going to have a part where you have your own thing to do. But the vertical does have something. It has gravity. Remember, gravity is -10 because it's down. We've defined down as being negative. So every time we're going to add this -10, so the vertical component, 30 plus -10 is going to be a 20 meters per second. You can see here it's going to be 10. It gets to the top here and we're at 0. But remember, we still have the horizontal. But I have a question. What's the acceleration of gravity right here at the top where the velocity goes to 0? Vertical velocity goes to 0. What's my acceleration? Does it go to 0? No, it doesn't go to 0 because it went to 0. It wouldn't come down. There. It stays at 10. 10. 10 always. 10 on the bottom, 10 at the top, 10 always. And we're coming down. Again, we're going to add another -10. So we have -10 meters per second. -20. -30 on that. Up's positive, down is negative. And when we get these things, notice how this original vector, the vector is, notice how it touches the parabolic curve. What do we call this geometric relationship? Starts with a T. The line that touches a curve at only one point is tangent. Yeah, they're tangent. All these vectors are tangent. And it is the slope of that tangent that gives us our speed. It's the slope of the tangent. It's the slope of this line. That is the speed of that particular, at that particular point. That slope. Positive slope, negative slope. But even positive, negative, it doesn't always go that way, because if I was going down, we might still think, well, I still have a positive slope. We look at whether it's positive or negative, because this vector here, right, this vector is going to be negative something because it's going down. These are positive something because they're going up. And you would apply that because we look at it, we say it's negative because it's going down. We say this by inspection. And we'll see that in a second when we start calculating these things out. So on the top, they've divided them up. Now on the way down, though, they want us to, basically, we are finding the resultant vector. Over here, we were resolving our vectors. Over here, they want us to find the resultant. What's this resultant vector down? Well, notice I have that horizontal, I have that vertical. They meet at a right angle. How do we find that? Well, we use this. Anybody remember what that equation is called? C squared equals A squared plus B squared? Pythagorean theorem. It's Pythagorean theorem. In fact, they even were nice about it. They kind of solved it out for you. The velocity vector, and that's what this resultant is. That velocity vector is equal to the square root of the Vx squared plus Vy squared. Remember, the Vx is that component. Y is that component. But, you know, when I square negative 10, it's going to become a what? A positive 100. But I know my resultant vector has to be a negative. Remember, that's direction. How does it become a negative? Well, we have to remember square roots. Remember, square root can be a plus or a minus. Remember, we tend to run over that. In fact, you know, in algebra, we tend to only take the positive. Remember, a square root can be a plus or a minus. You know, on that. That's why the quadratic equation, you know, it's but negative b plus or minus the square root of b squared minus 4ac. You know, why is it plus and a minus? Because the square root can be a positive or negative. This side would be the positive answer. Going down is the negative. So what you guys are going to do with your group is you guys are going to find the resultant vector in those three using the Pythagorean theorem. So front table, move to the back table, and you guys all solve these out, please. I'll give you a few minutes to solve those out together. So let's look at this. So here I have 10 squared plus y squared, so 100 plus 5. So I have the square root of 125, which I believe is 11.2? 11.2 meters per second. But plus or minus, it's a negative. It's a negative 11.2. That vector there is the positive 11.2. Same level, same speed, but different velocities. Notice they both have a speed of 11.2, but this is a positive where the other one is a negative velocity. Remember, the speed. Speed's the how much part. Whether you're going up or going down, speed. Doesn't matter what direction, but velocity needs a direction. Here at 20, 20 squared plus 5 squared would be the square root of 425 plus or minus, so it's a negative 20.4 meters per second. Negative. Over here, this vector is the positive 20.4 meters per second. There, same level, same speed, different directions. Here at the bottom would be the plus or minus the square root of 925, which is we'd have negative 30.2 meters per second. This one would be that positive 30.2 meters per second on that. And also notice how the resultant is getting closer and closer to the y component. If we went down to the next one, or is it, no, I think that's 20.6, isn't it? 20.6, 30.4, something like that. But you can see how it's getting closer and closer each time. Now, is it ever going to get the same? No. Remember, you always have this little bit here. I mean, at some point, you might have a vector that looks, you know, something like that. You know, very long x component, very small, very long y, very small x. It's never going to get the same, but it's going to become closer and closer to vertical, even though it's not going to get there on that. Any questions on the concept builder? Remember, this is part of your notes. Remember, anything that doesn't have a stamp is part of your notes. So let's go back up. We're going to kind of finish up our notes here. All right. So remember, we did talk about, last thing remember we talked about was this, about real path, how you'd be inside, right? About that. That was the last thing. So let's talk about this ball. A ball is thrown horizontally. I don't think we got to this, did we? If the ball is thrown horizontally, in other words, I'm giving all of the velocity here is in the horizontal. It's all in the Vx direction. There's no Vy. There's no down. It's just like dropping the ball. If a ball is thrown horizontally, it would only travel outward as long as it's in the air. That makes sense, right? It's only going to get, however long it's in the air. But it's the y component. It's this vertical distance. In other words, the time it takes to fall in the vertical direction that's going to determine time of flight. In other words, it's the y component that determines how long you're in the air. Okay, it's this y component on that. So in this case, if I want to know how long is this ball going to get in the air, how long does it take to get to this point at 20 meters? Anyone, how long? From this picture, how long does it take to get to that point? Remember, it takes as long to get to that point as it takes to fall vertically. How long does it take to fall 5 meters? It takes 1 second. 1 second. Remember, this is how far we fall in the first second of free fall. That's why we should kind of learn what those first 5 seconds. Remember, first second we're going to be at 5. Second we're at 20, 45, 80, 125. Those are the first 5 seconds of free fall. Which means, what did that velocity have to be? Well, if I traveled 20 meters horizontally in 1 second, 20 meters divided by 1 second, I must have been going 20 meters per second. If I change this problem a little bit, let's say this was a 20-meter tower. If it was a 20-meter tower, then it would have taken me 2 seconds to get to the bottom, in which case it took me 2 seconds to travel that 10 meters, in which case that would be 20 divided by 2, or 10 meters per second. All right, so once we find out how much time, we can find out that horizontal velocity. Now, get out Concept Builder 3-1. The very bottom of the back side of 3-1, there's a thing there. Does anybody need more time on this slide? Okay. So while you guys are finding the other one, we'll pause there for a moment. We have this thing that looks like this. So you are an accident investigator, and by the way, do not read in the problem, just take it for what it looks like. Whether or not this guy was speeding before it crashed through the rail of the bridge into the mud bank. So notice our bridge is 4.9 meters above. Think about what that is. By the way, this is real world data. We'll talk about that in a minute. But by the way, how much difference is 4.9 meters to 5 meters? That much. That's the difference between 4.9 meters and 0.1 of a meter is about that far. Okay, so keep that in mind. It's not very far. So the time it took to fall this 4.9 meters, it went out to 24 meters. So based on what we learned in that last slide, you guys determined, was he speeding? If he was traveling at 55 miles per hour, that means 24 meters per second. So if he was faster than 24 meters per second, he was speeding. If he was slower, he wasn't. So work with your group, take a couple minutes, and see what you come up with on that. So, was this guy speeding?
Yes.
Well, to fall 4.9 meters takes how long? 1 second. I understand. Mr. Reese, you said we fall 5 meters in 1 second. Now remember, the acceleration of gravity is actually 9.8 meters per second squared, which we approximate to be 10, right? We use that approximation. So remember, we said, okay, in the first second you fall half that number in meters. What's half of 9.8? In reality, you fall 4.9 meters. But remember, what's the difference between, it's 1 decimeter. 10 centimeters is the difference there. So it's not going to make a difference. So it takes you 1 second to fall. And if I travel, so that means it takes 1 second to get to that point like that. It took 1 second to go to those 24 meters, which means this guy's velocity, 24 meters divided by 1 second, or 24 meters per second. Was he speeding? No. At least he wasn't speeding after he went through the rail. Like I said, that's why I say don't read through the thing, because if you crash through the rail and we're 24 meters per second after you crash through, that means you're probably 20 more than that before. But that's really the thing. We don't know. We actually don't know. There might have already been a hole there. For all we know, there was already a hole there. But the answer is he didn't. He came at the same speed. All right, questions? All right, so let's go back to our notes. All right. So here, now there's another thing. To go into orbit, orbital speed. This has to do with orbital speed as well. To go into orbit, you have to miss the Earth. That doesn't mean, boo-hoo, I'm homesick, I miss the earth. No, that's not what we mean. It means as you are falling, you miss the earth. Like if I threw a ball at Adrian and I don't hit him, I missed him. Okay? So what are we actually looking at? And I'll come back to this. But even Isaac Newton, way back when, said, you know what? If I took a great big cannon and I put it on top of a mountain, if I fire this cannon, you get a ball horizontally, the ball's going to follow that parabolic arc down. If I get a bigger cannon and a bigger cannon, well, eventually I might get a cannon big enough that as this parabolic arc is going, the earth curves. It curves out from underneath, and I end up going around in a circle like this. In other words, it's always falling. It doesn't hit the earth because the earth is round. I mean, if the earth was flat, it would have hit the earth. But it's not flat, and so it curves out from underneath. Remember, the ball, this thing is only falling at a certain rate. Remember how many meters? So if we thought, how many meters below are we, 5 meters, 20 meters, and so on. So it's falling down below that path, right? If the earth curved more than that falling path, we're going to go around. This is the whole idea of putting something in orbit. And it turns out that the curvature of the earth drops 5 meters when you have traveled out 8 kilometers. What does that mean? So if I took something and this board was fixed to a star, because technically level on the face of the earth means curved, right?
Yes.
Now we live on a curved surface. We don't notice it because from our perspective it doesn't seem very curved, but it is a curved surface. We're talking if we locked ourselves on a star and we were going to go straight out. When we had gone out 8 kilometers, and this is not the scale, when I've gone 8 kilometers out, I would now be 5 meters above the surface of the earth because the earth, as it curves, is going to go away. Which means if I had a projectile and I fired my cannon, there, it's going to fall, and after 1 second, if I could get beyond this point in 1 second, which is how long it takes to fall 5 meters, would I ever touch the ground? No. Which means if I can go 8 kilometers per second velocity, which is about 18,000 miles per hour, somewhere in that ballpark, about 18,000 miles per hour, I'm not going to hit the earth. By the way, any idea how fast space shuttles and space stations and satellites go around the earth? Take a wild guess how fast they're moving. They move at about 18,000 miles per hour. Now, trouble is, which means, can I just take my rocket and put it on a stand and launch it horizontally from Cape Canaveral? I mean, they launch it straight up. Why launch straight up? I just launch it vertically and I get really low orbit. Really low orbit. What would happen to something going 18,000 miles per hour in our part of the atmosphere? It would melt. It would do more than melt. It would burn. It would burn up. Think about spacecraft coming back into the Earth. I mean, those heat shields and things like that, they're heating up way up high in the atmosphere. Is there very much air there? No. It's like it's almost no air there. Still, it heats them up enough that they have to have heat shields. We actually lost the space shuttle because it heated, had damaged heat shields and things like that. And there's very little atmosphere, so this is why. So that's why they launch things vertically. Is we launch it vertically until it gets up above most of the atmosphere, because when it's down here, it's moving pretty slow. So by the time it gets up to that 18,000 miles per hour, it's way up here, and then it goes horizontal. So we launch it vertically to get up above most of the atmosphere, and then it goes over horizontally to go where it needs to go. We launch from Florida because we launch over water. to go into an orbit around the equator, we launched from Florida on that. Closer to the equator, the better. Where they launch is pretty much the most southern part of the continental United States. They actually considered launching from Hawaii at one point on that. To launch polar orbits, so that those are orbits that go around the equator. To launch, anybody know where we launch polar orbits? I mean, we launch satellites that go on from pole to pole. We put spy satellites. We put things like Landsat satellites that investigate, that basically like map the Earth to find resources. Because polar orbits, eventually you will pass over every single point of the Earth. Things along the equator do not do that. Anybody know where we launch rockets to put on polar orbits? What? Well, no, it's in the United States. It's a lot closer than you think. Actually, we launch it from Vandenberg Air Force Base. Vandenberg Air Force Base is in Lompoc, California, near Santa Barbara. It's just north of Santa Barbara. And I'd say Lompoc is about maybe 3 hours south. It's a little south of Pismo Beach. So we launched that there. They actually built a shuttle facility. They actually built a space shuttle launch pad there, but they never used it. But if we ever had to put a space shuttle on a polar orbit, that's where it would be launched from. Because from there, when they launch over water. The whole idea, launch over water. If you have an accident, it falls in the ocean, and not on people. Being in the military, my car insurance actually has a thing about, if you get hit by, it has things about being hit by nuclear weapons and things like that, because my insurance company only insures military people. So there's things about if your house or your car or whatever gets destroyed because of warfare, like it doesn't get covered. Things like that. Yeah, there's actually a thing about nuclear weapons and stuff like that in my insurance policy. All right, that's actually about it. So let's get out your concept builders, your 2-2 concept builders. We're going to look at 2-1 and 2-2, look at a couple of things, and we're going to watch this video. Okay, so we're not going to go through everything, but we're going to hit a few of the high points. The first part is about a constant velocity. Remember, the idea of a constant velocity is you're going to cover the same distance in every segment of time. They showed you that you traveled 1 meter in 1 second. So every second we're going to cover 1 meter, no matter what, because we're going at constant velocity. So our velocity would have been 1 meter per second, because we traveled those 5 meters in 5 seconds. But each segment we're going 1. Table, that should have been pretty easy, just velocity equals distance divided by time. They gave you 2, solve for the other 3. Now this thing, many of you had some troubles with this. They told you in the problem that it had an acceleration of 2 meters per second squared. We do a lot of things with ramps because it's very hard to investigate just dropping the ball. I mean, even from the highest point of the room, it's not 5 meters. I mean, the highest point of this room is not 5 meters, so there's less than 1 second of free fall, even from the highest point in this classroom. So it's very hard to investigate, but we use ramps. We get the same relationships, so we're kind of slowing things down by using the ramp. Now this ramp was set so acceleration due to gravity would be 2 meters per second squared. Now remember, that means I'm getting 2 meters per second every second. All right, so right, 0. After 1 second we went to 2. After 2 seconds we'd be at 4 meters per second. Then 6, 8, 10. Okay, so we got that. Then they want us to look at how far are we going each segment, each second. How far are we going? Remember, we're going a little farther each second. Now remember, there's two ways to do this. One, we can remember, well, each second I'm basically adding the acceleration to it. There, when we talk about gravity, the first second is 5. Then we gain 10 every time I add that. So it's 5, 10, 15, 20, or excuse me, 5, 15, 25, 35, and so on. This one we're going to gain 2. So the first segment is 1. The second segment would be 3, because we add 2. Then 5, 7, 9. So we gain 2 every second. We're going to go 2 meters farther in each additional second. Or we could do it the other way we did it, and that's find the average. How is the average speed? Whatever the average speed is for that second, that's how far you're going to go. In the first second, 2 plus 0, the average is 1. 2 plus 4 is 6, the average is 3. 4 plus 6, 10, so the average the average is 6 plus 8 is 7, the average of 8 and 10 is 9. Then they wanted you to do how far down below? We just add them. 1 plus 3, 4. 4 plus 5, 9. 9 plus 7, 16. 16 plus 9 is 25. But look at these values there. They're all what?
No, 16 is definitely
4 and 16 are not odd, but they are what? 1, 4, 9, 16, 25 are all perfect squares. They're all perfect squares. This is the relationship that Galileo found. Now, Galileo didn't have stopwatches. He used bells. There's a thing about, a lot of physicists tend to be very good musicians. Something goes along with that, And what Galileo did first, he put his bells like you marked your ramps. He put them at even intervals. But when he ran the ball down, he hears ding, 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 ding. The bells got faster. So he said, well, what if I space them so all the bells ring evenly? In other words, the first ding, 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 ding. So the bells had to get farther and farther apart, and he found that they had this ratio of perfect squares. And as he did more things, we more commonly look at it this way, though, that distance is directly proportional to the time squared. Which is the answer to your lab? In the lab, this is the one you should have had, the straighter line. It should be a straight line, but it's straighter line. All right, distance is directly proportional to time squared. And if we saw this, if you remember the formula, 1/2 g is just a number. D is a number times time squared. Another way to look at this acceleration times time is velocity. So if we write it like this, velocity times time is distance. I mean, it's still the same relationship as you have on that. Now, your labs. Now, there are a couple of things I want to mention about your labs. One, the graphs. A lot of times we do these relationships where we're looking for one is directly proportional and one isn't. Now, a lot of times if you just put the two graphs side by side, one is going to be a lot more curved than the other. And so you say, okay, the one that's less curved is the one it is. Because generally you're never going to come out with a straight line. Just usually doesn't happen. Some of your graphs, it would have been very hard to tell. How are they right? Oh. I didn't write it the way you're used to seeing this. In your book, when you go to algebra, you're used to saying y equals ax squared plus bx plus c, like that. I write it like that. This is the way the computer, your graphing program, writes out the quadratic. And specifically, we are looking at this value. The smaller the value for C, the absolute value, it could be a positive or negative. The smaller the absolute value of that number, the straighter the line, in other words, less curved. So in other words, if you have two graphs, you look at your two graphs, and you can't tell which is less curved, you're going to look at this value of the quadratic. And the one that has the lower c value is the one that's straighter. It's a math thing, but it helps you do that. Because if the c term went to 0, which is as low as it can get, notice what are you left with? Y equals a plus bx, which is the formula for a straight line. Remember, when c goes to 0, you get a straight line. So when you have the two quadratics, which happens a lot just because of the material we use, you're looking for the one with the smaller value of c. Now, although you cannot compare errors, you can compare the c values. Also, many of you did not write give me the sample equations. You know, the samples, you lost points there. Make sure you're doing that. Also, do not try to incorporate the previous lab or exercise into the current lab. Yes, we did 2 labs where we took times on ramps, but they both had different problems and we were using the data differently. And people tried to give me velocity. And by the way, when I talk about these things, generalities, I'm talking about all 3 physics classes, okay? And there are 3 physics classes. These are things I noticed when I grade them. Because I just usually have a big pile of labs and I just grade them. I don't really look at what class is doing what. So there's people in all the classes that do these things. So, 1, answer the problem you're doing on the lab. Don't try to apply what we did before. In the exercise, we were dealing with velocity and acceleration. In this one, we were dealing with displacement and time. So, different things. Also, in exercises, remember when we do things in the notes, we will make one data table, one data and calculation table. It's one big table. Okay, that's fine. That's for the exercise. Lab reports, remember, observations have their own set of tables that belong in observations. Calculations have their own calculation tables that are in calculations. Do not combine them. There were a number of people who wanted to put average time at the end of the observation table. I saw that a lot. Probably you guys see a big scribble through it. Okay, you know, on that. You lost a half a point on format on your rubric score. So make sure you get those in the right place on that, okay? More details, some of you did that. Also, putting that for title. Also be careful which axis. There were a number of people who put time and time squared on the x-axis. Maybe we put time when it's a rate. This time the lab procedure sheet even told you distance on x, time and time squared on y. So be careful when you're doing your graphing. All right, so these are things from this lab that I noticed, and I think we need to improve on that. Every time our goal is to improve and write better lab reports. All right, 2-2, backside. Backside of 2-2. The charts. This one gets people. This is why I give this one. Now remember, our graph is only recording even a whole number of seconds. The graph is only telling us what's going on at whole number of seconds. What's our velocity and what is our displacement? Because although it says distance, we're really looking at displacement, how far above or below our starting point, because we're throwing the ball up and sometimes it actually goes below our starting point. Gravitational acceleration, -10 meters per second squared. So we throw the ball up at 35. Remember, we're always adding a -10. So 35 plus -10 is 25. Plus -10 is 15. Plus -10 is 5. Now this is where people got in trouble. 5 plus -10 is... Does that mean it didn't go to 0? No, but it went to 0 in between. Now this only tells what happened at 3 seconds. Where was I at 4 seconds? I was at 0 somewhere in between. Now the first two, yes, 0 height and 0 velocity occurred on a whole number second, because we started at 40 and 30. If it ends in 0, you're going to do that. If I'd given you 42, it wouldn't have ended that way either. You know, it's only because if you start at 30, 40, 50, things like that, it will end up that. Any other number, it's not going to do that. Why have you wanted to put 0 in? Follow the math. So so the ball went up, came down, so now we're going -5, -15, -25, -35, -45. Okay, on that. Then distances are displacement. Remember, some of you I think wanted to add them all up. That's not, it wasn't following the path. They really wanted the displacement. It really should say displacement, not distance. So remember, we go 35 plus 25, our average is 30. So we went 30 in that second, 0 plus 30 is 30. In this second, we went 20. 30 plus 20 is 50. We went 10. 50 plus 10 is 60. Now here I might get in trouble again. 5 plus -5 is 0. 60 again. Now does that mean I went up straight across and came down like that? Again, we got to the high point somewhere in between the third and the fourth second. Somewhere above 60. Again, then we have -10, or 50, -20, 30, -30, we're at 0, and -40, we're at -40. Notice, same speeds. 35, 35, we're at 0. 25, 25 at 30. 15, 15, 50. 5 and 5, 60. Here we're below, so if this was like a cliff, we threw it up, and then it went down. So time 8 was somewhere below. We said 0 is right there. Anything above is 0. Anything below is positive. Anything below is negative. Any questions on those? Okay, so we are going to watch the video. The video is a review, so we're taking Cornell notes at the end. Well, you guys are going to, while you're writing summaries, I will come by and stamp them. They go in your classwork packet. This is called linear motion. The video is by the author of the book, and they're a little old. This is him actually lecturing to his junior college class in Hawaii. He actually he developed this program at San Francisco City College. This course in college is euphemistically sometimes called, physics for poets. Because this would be, if you were a non-science engineering type major, this would be a science that you would take to fulfill your science requirements. Conceptual physics, algebra-based physics. That's what it was developed as. It was originally a college course. It was applied to the high school. And, by the way, he is a, you can say, die-hard kind of hippie. How he talks. By the way, how he talks in the video is how he really talks. I mean, if you meet him, and I've met him and I've talked to him, the way he talks to his class is how he really talks. Okay? So on that, he's a lot older. These videos, I think these ones were like late 90s, early 2000s. When the videos were actually made. They're in Hawaii. By the way, he makes lots of references to Hawaii because he's in Hawaii. There are things that are in Hawaii that are very different. They don't have things that we have here. Like, they don't have an amusement park in Hawaii. There's no, theme park in Hawaii. Although you can consider that the entire island of Hawaii, the whole state is a theme park, on that. So keep in mind these things. So just taking notes.